welcome to another module in this massive open online course. Alright, so we are looking at the mutual information, we have looked at the properties of the mutual information, the definition, the properties and the relevance of mutual information. Alright, and let us now look at one of the most important and landmark results in information theory, which relates to channel capacity and which depends on the mutual information. Okay, so what I want to look at today is one of the fundamental results information theory. As I already told you, this is one of the fundamental, I can also say the landmark results. One of the fundamental results in information theory, which is concerned itself, which can be described as follows, that is, if I have a channel and this can be any, and I have an X which is the input stream and Y which is the output. Okay, this is your communication channel and described by the transition probabilities Py given X, that is the probability that the output takes a certain value corresponding to a given input symbol. Okay, so the channel is described by a set of transition probabilities, correct. And we already have seen what is the mutual information. The mutual information, remember we said this has a fundamental role to play in defining the rate at which information can be transmitted across the channel. This is Hx minus Hx given Y is also equal to Hy minus Hy given X. Okay, so if you look at this, this is basically the uncertainty in X, uncertainty in X or uncertainty if you look at Hx, let me just repeat that logic again. If you look at simply Hx, this is the uncertainty in X Hx is simply the entropy or the uncertainty in X, that is the input symbol stream X, the input X. Okay, Hx given Y is uncertainty remaining in X or the entropy in X conditioned on Y, that is on observing Y. So, this Hx given Y uncertainty in X on uncertainty in X on observing Y, which means if you look at this I of x y, which is Hx minus Hx given Y, this is uncertainty in X minus uncertainty remaining in X. So, this is basically uncertainty resolved, uncertainty about X that is resolved on uncertainty about X that is resolved on observing Y. And we said that for a good channel this should be high. alright. For a good channel, this quantity should be high. That is, we would like to make this mutual information between x and y. Mutual information of x and y is nothing but the information, that is uncertainty in x that is resolved by observing y, or uncertainty about y that is resolved on observing x. That is, you can also say that is how much information is basically conveyed regarding x by y, how much information about y is conveyed regarding x, okay. And therefore, we want this quantity to be high, and in fact the fundamental result for the capacity of the channel, for the channel capacity, the fundamental result for the channel capacity, this states that the maximum rate of information transfer across the channel is given by the maximum of the mutual information, where the maximum is taken over all the input probability. In fact, this is one of the most fundamental. The channel capacity is the maximum of the mutual information. We can call this as C equals maximum of the mutual information between input and output, between input x and output y, and this maximum, remember this maximum is taken over all, maximum over all input, that is probability that is, what is the input probability distribution for which the mutual information is maximized. That is the capacity of the channel. The units are bits per channel use or bits per symbol. Bits per symbol transmitted, and it is important to understand what this channel capacity denotes. This channel capacity denotes, or the C, the channel capacity C, this denotes the maximum rate at which information the maximum rate at which information, this is the maximum rate at which information can be transmitted, this is the maximum rate at which the information can be transmitted, maximum rate at which information can be transmitted over the channel. This is in bits per channel use, that is the maximum number of bits per each symbol, that is the maximum number of bits that can be packed over each symbol that can be transmitted over the channel. And needless to say, this is a landmark result because this characterizes in a fundamental way what is the maximum, that is information rate, what is the maximum bits per second. For instance, we have several communication systems such as 3G, 4G, 5G, right. One would like to know what is the maximum rate at which information can be transmitted over the channel in each of these communication systems, and this framework, which is the channel capacity, gives us a very central result, a landmark result to characterize the maximum rate. and most of you must have heard this result is due to none other than, well, the very celebrated figure in information theory. So, this result is due to the well known scientist Claude E. Shannon, and so this is the Shannon's result on the channel capacity, and Shannon is also, as must be known to many of you, is known as the father of information theory. He was a person who originally developed this framework of information theory, which right now has grown to include and grown to have applications in so many diverse areas. One of them is of course in wireless communications, but it can be applied in many other areas. So, he is known as the father of information theory, and this result was published in the channel capacity result was published in the landmark article titled originally published this result was originally published in the landmark article, or basically let us say the landmark paper, landmark research paper titled, and the title is a mathematical theory, which was later changed to the mathematical theory. A mathematical theory of communication. Okay, so it was originally published in this landmark research paper, and needless to say, the channel capacity is a central result in one of the central results in all of communication theory, because it helps characterize in a very fundamental way what is the maximum rate at which information can be transmitted in bits per channel use, and naturally we are going to see later that can also be extended to bits per second across a channel. So, it is a fundamental result. Okay. So, this channel capacity, I cannot overemphasize this, I cannot emphasize this enough. This is a fundamental, as far as fundamental results go. There cannot be any more a result which is more fundamental than this. So, this is the channel capacity, is one of the fundamental results, in fact one of the fundamental results in modern communication theory. One of the fundamental results in modern communication theory, all right, characterizes the maximum rate of information transmission, correct. It has led to the development of several modern communication systems or several modern techniques. It has led to development of techniques for modern wireline both, wireline slash wireless communication. And more importantly, this is also all the channels result. If you look at it, it says that there exists, that is, it is possible to transmit information at this rate over across the channel, but it's not explicit about what is the technique that can be used to transmit information at this rate over the channel. So that calls for the design of techniques which make possible, right, robust codes which make it possible to transmit information at this rate given by the maximum of the mutual information or the channel capacity across the channel. So that has to lead to the development of several efficient techniques or error correcting codes to enable one to transmit, push closer and closer to the channel capacity or transmit information at this maximum rate. Okay, so this channel capacity has also led to, because performance of every error correcting code can be benchmarked against that of the channel capacity, it has led for achieving capacity. When we say achieving capacity, we mean that basically transmission or basically transmitting information at rate and another interesting aspect of the channel capacity is also that at this rate C, it guarantees that if you look at this channel capacity C, guarantees information can be set at an arbitrarily low probability of error. That is, this is the rate at which information can be sent over channel with arbitrarily low probability of error. And this is the keyword, arbitrarily low probability of error, implying that I can keep devising better and better schemes such that the probability of error is driven close to 0, not exactly 0, but it can be driven as close to 0 as one wishes by devising better and better scheme. In particular, considering larger and larger block lengths over which the symbols can be encoded. Okay, so that is one of the key results, key legacies of this information theory and Shannon's paper, the mathematical theory, a mathematical theory of communication, which comes up with a framework of information theory and fundamentally characterizes the maximum rate at which information can be transmitted over any given over this channel, which is also known as a discrete memory list channel, although we have not gone into the details of that, right? It is basically given by the maximum of the mutual information, where the maximum is with respect to all the possible input source distributions, that is the input symbol distributions, okay, input alphabet probability distributions. Okay, to just take an example for channel capacity, let us go back to our binary symmetric channel and quickly look at what we had yesterday. Let us go back to our BSC, that is your this is your binary symmetric channel where you can have 0 and 1 with probability alpha, input symbol 0 and 1, and correspondingly you can have output symbol 0 and 1. The direct probabilities are 1 minus p, 1 minus p. The crossover or the flip probabilities are basically p and p. You can receive this as 0, you can receive this as 1, this is x, this is y. This is symmetric because the flip probabilities for 0 and 1 are the same, the direct probabilities for 0 and 1 are the same. So, this is your binary symmetric channel model. And we have seen the mutual information, right. In the previous module we have calculated the mutual information of this channel, mutual information between the input and output for the given probability, the flip probability p and the input probabilities alpha 1 minus alpha. Okay. And we have seen that the mutual information equals h of alpha plus p minus 2 alpha p, this is h of alpha plus p minus 2 alpha p. Remember, this is your h of y minus h of p. This is your h of y given x. Okay. Now, if you look at this h of p, realize that this is a constant for a channel. H of p equals a constant, because for a given channel, that is probability is p, this depends only on p. So, the rest, so when we are trying to maximize the mutual information with respect to the source probabilities, and remember the source probabilities are characterized by alpha. So, I can write this capacity as maximizing IXY mutual information with respect to alpha, because alpha completely characterizes the source probabilities, because source given alpha I can derive the source probabilities are alpha and 1 minus alpha. So, maximizing the mutual information with respect to the source or the input probability distribution is the same as maximizing it with respect to alpha, correct, because alpha is the parameter which completely characterizes the input probability distribution. So, maximize because alpha completely this is equal to, therefore, max alpha h alpha plus p minus twice alpha p minus h of p. Now, h of p is a constant, so I can just look at maximization of h alpha plus p minus 2 alpha p. Now, we know that this maximum occurs for alpha plus p minus 2 alpha p equals half. And considering the symmetry, if we set, remember everything is symmetric, so it should be obvious what is the value for which it's maximized. Considering symmetry, if we set alpha equals half, then alpha plus p minus 2 alpha p equals half plus p minus 2 into half into p, which is half plus p minus p, which is equal to half. So, we obtain h of half, which is equal to 1, which is the maximum value of, which is indeed maximum value of h of alpha plus p minus 2 alpha p. Because remember, we have said that the entropy of a binary source, that is h of 0 it is 0, h of 1 is 0, at 0 is 0, at 1 it is 0, and achieves its maximum at corresponding to the when the binary source alphabet, like each of the alphabets in the binary source alphabet has probability half each, alright. And we have shown by choosing alpha equal to half, we are able to achieve, right, h of, so we are able to achieve h of half, which is basically equal to 1, which is the maximum. Therefore, the maximum, so therefore now we get C, which is equal to maximum over alpha, the mutual information is equal to maximum over alpha h of alpha plus p minus 2 alpha p minus h of p, and the maximum of this is basically occurs when alpha is equal to half, which is equal to h of half minus h of p, but h of half is 1. So, this is 1 minus h of p. So, C equals 1 minus h of p bits per channel use, C equals h of 1 minus h of p bits channel use for binary symmetric channel. Okay, so this is the C is the maximum rate of information transfer. Again, needless to say, we have said this several times, this is the maximum rate. We have not formally proved this because that is a very involved proof. So, we are taking this result as given. This is the maximum rate of, that is the maximization of mutual information, is a very involved proof. This is the maximum rate of information transfer over BSC, that is equal to 1 minus h. So, we have not seen a formal proof of that statement, that is the capacity is the maximum rate at which information can be transmitted over the channel, which follows from Shannon's theory. Of course, Shannon has given a detailed proof, all right, for this statement or for this result. However, in the interest, because the scope of this course is limited, all right, so we will not go into the details of the proof and will rather take it as a given that this is the result which governs the maximum rate at which information can be transmitted, and employing this result we have found that basically the maximum rate at which information can be transmitted across the binary symmetric channel with flip probability p is 1 minus h of p. And needless to say, of course, h of p, and you can say several things from here. First of all, h of p equals h of 1 minus p, we have already seen that h of p equals h of 1 minus p, which implies the capacity of a binary symmetric channel with flip probability 1 minus p, that will be 1 minus h of 1 minus p equals 1 minus h of p. So, this is capacity with flip probability with flip probability equal to 1, and actually because it is symmetric channel. So, if flip probability 1 minus p, you can see, you can reason that it is similar to having a binary symmetric channel with flip probability p. So, both these channels have the same, have an identical capacity, which is 1 minus h of p, or 1 minus h of 1 minus p, which is basically the same as 1 minus h of p. And before we complete this module, two special cases. One, capacity is maximized for p equal to 0, in which case C equals 1 minus h of 0 equals 1 minus 0 equals 1 bit per channel use, and also by symmetry p equal to 1, C equal to 1 minus h of 1 equals 1 minus 0 equals 1. Okay. So, for both capacity is maximum equal to 1 bit per channel use. Which is something very interesting if you think about it, because p equal to 0 is fine, that is there is no error in the channel. A 0 is always output, the output corresponding to 0 is always 0, and a 1 is always received as a 1. But the case corresponding to p equal to 1 is very interesting, because 0 is always received as a 1, alright. With probability 1 it is flipped to a 1, 1 with probability 1 is flipped to a 0. So, the channel is always flipping a 0 to 1 and 1 to 0, and you can see, you can clearly reason out that this case is also identical to the previous case. That is, so there is a certain symmetry about, although it is counterintuitive, there is a certain symmetry about the p equal to 0 and p equal to 1 scenarios, and in both these scenarios the channel capacity is exactly 1 bit per channel use or 1 bit per symbol. However, the minimum capacity occurs naturally for p equal to half, c equals 1 minus h of half equals 0. That is, information rate is 0 bits per symbol, that is you cannot transmit information. So, what the channel is doing is with probability half flipping 0 to 1, with probability half it is transmitting 0 as a 0. Similarly, for a 1 with probability half it is flipping 1 to a 0, with probability half 1 is received as a 1, and this turns out to be the worst possible channel in which, for which the capacity is 1 minus hp, that is 1 minus h of half, which is 1 minus 1, that is 0, which means no information can be transmitted in across this channel, that is 0 bits per symbol. Okay, that is the information, that is the rate at which information can be transmitted is 0. So, these are the interesting results, and therefore, there are several cases. Of course, this is only for the binary symmetric channel, and there are several other channels, for instance several such as an erasure channel, typewriter channel, so on and so forth. There are several other channels for which such interesting results can be derived. Of course, the most fundamental result is the capacity, the channel capacity result, which can be applied to a variety of channels to then derive what is the fundamental rate at which information can be transmitted across the channel. There is one other important channel which is employed frequently in practice, that is the Gaussian channel, additive white Gaussian noise channel, alright, which basically concerns itself with what is the maximum rate at which information can be transmitted over a channel which is affected by additive Gaussian noise. So, that requires some more theory in the form of differential entropy, etc., which we are going to start looking at in the subsequent modules, towards basically finally characterizing what is the capacity of this one of the most popular and one of the most relevant channels for a communication system, that is the additive white Gaussian noise channel. Alright. So, we will stop here, and I would like to request you again to go through this module to understand the importance of this result on channel capacity, and also the implications, and if possible to also try to go over the salient aspects of the proof of this channel capacity on your own, although we are not going to cover it. Maybe you can look at textbooks such as, for instance, the textbook on information theory by Cover and Thomas, etc., and try to get a glimpse of this fundamental, of the proof of this fundamental result, and also the capacities of various other channels. So, we will stop here. Thank you very much.